Good day, everyone attending remotely. This is a 101 course, Space Communications and the Interplanetary Internet. And I'm going to start with an extreme example of space communications. And that's, as many of you know, I'm going to talk about, I would say, probably my favorite spacecraft. And I'm sure it's the favorite of many of you is Voyager 1. Basically the first human-made object that basically left the solar system. Think of it that it was launched 47 years ago, and it reached interstellar space more than a decade ago, actually in 2012. But now coming back to communications, just wanted to let you know some of the very extreme measures that constitute, the Voyager operations. The first one is the distance from Earth. It is more than 15 billion miles away. That's basically, 166 astronomical units. And it moves pretty fast, 30,000 miles per hour. And I think it's 38,000, but let's say I think it's 38,000 miles per hour. And then one very important thing is basically we have to wait close to 2 days to see if we're able to communicate with Voyager. That means that the round trip time, which is the time it takes for us humans to send a signal to a spacecraft and receive it back, it's 46 hours. So the one-way light time is 23 hours. It's a very long time. Put this in construct with how immediate are communications on Earth. When we look at the specific in communications, this communicates on the microwave X-band right now, 8 gigahertz. But one of the things I want to highlight here is the signal level or the power received on Earth. Voyager has a 23 watts transmitter. But basically, we received a billionth of a watt, and that's termed an attowatt. So very, very, very faint signal, but thanks to the Deep Space Network, we're able to decode the signal, demodulate the signal, decode the signal, and obtain information. How much we get, give or take, in normal operations is around 160 bits per second. But every bit that we receive, it's literally new information for humankind. That's how important this data is. So when we look at the Earth orbit, and it started with the International Space Station, this is in the low Earth orbit, which is one of the closest orbits to Earth, 250 miles away. And in that case, the delay experienced in communications, which is basically how long it takes for the signal, which travels at the speed of light, from ground to the station or from the station to ground. And in this case, it takes, in the tens to hundreds of milliseconds. Then when we move further orbits, like the geostationary orbit, which is 36,000 kilometers or 22 miles away, then 22,000, miles away, then we're talking about several hundreds of milliseconds. So the delay continues to increase. But in that case, what happened is that the longer the distance, the more signal or energy or power is lost. Because we're talking about the interplanetary internet, let's focus around the solar system. And the first, planetary body satellite is the moon, which is, around 240,000 miles. And in this case, the signal delays are no longer milliseconds, but are on seconds. So one-way light time to the moon is around 1.3 seconds. But if you take a second example, which is Mars, which is the next planet, we're talking about millions of miles, depending on where we are in this 2-year cycle between Earth and Mars. The distance goes from 35 to 250 million miles. So we're not talking about hundreds of thousands anymore. We're talking about millions or tens of millions or hundreds of millions of miles. And what happens in this case is that now we're talking about one-way communication delays for one-way communication delay of minutes, several minutes. And then if we start looking at the outer planets, we talk about delays of hours. And let's close with interstellar space, where Voyager is today, and I'm thinking about the next star. And now we talk about trillion miles. So this tells us that the space volume is huge. But now the delays, we talk about days to years, depending on where, how close or how far that spacecraft would be in the future. So there are two realities here. The first reality is that real-time communications, or what we as humans understand as real-time communications, is no longer possible. Because, for example, if you are in communications with the moon, whatever information you receive happened at least, let's say, 2 seconds ago. If you are on Mars, if you're receiving communications from Mars, whatever information you received already happened 6 minutes, 20 minutes ago. The second part of it is what we have to do to receive that communication, to demodulate that communication. So basically extract information out of it. The longer the distance means more dollars, larger investments. Why? Because you need bigger antennas. We're talking about microwave bands. Parabolic antennas are the highest gains. You need a larger and a larger and a larger and a larger dish, which means, level of investments that are very, very high. Just to give an idea, the largest antenna that we have till now for radio communications in the DSN is around 70 meters. That's the size of a football stadium, and I don't know how many tons of weight. It's but not only it's the fact of real estate or how big the antennas are, but also the electronics. We start talking about electronics that requires close to zero noise or very, very low noise, and because of the law of thermodynamics, that means that you need to put those electronics at very, very low temperature, which talk about cryogenics electronics, and that also has a cost implication to it. So it's as conclusion, the effect of distance is twofold. On one hand is communications. There is a delay, inherent delay of communication just because of the speed of light. And the second is that there is a huge signal loss that you have to compensate basically with money to have better transmitter, better receivers, larger antennas. So that's the first major effect is distance, the volume of the space. The second major effect or cause in this case is disruptions. And that's caused by celestial mechanics. In space, everything is moving. Galaxies are moving, and within the galaxies, solar systems are moving. Planets are rotating. They are moving or translating between each other. There are effects like conjunctions where planetary bodies may not be visible because there might be something else in the middle, another planetary body, which is, for example, when you think about the Mars solar conjunction. And the effect that everything is that all these celestial mechanics create is disruptions in the communications. There is no line of sight because at the end of the day, radio waves in general communicate via line of sight. So each point has to see each other. In the case everything is moving or rotating, that inherently create a disruption and then loss of signal, loss of communications. And that's a great example when we think about communicating to the moon, to Mars, for that matter. So let's see how we compensate or how we handle those two main effects: delay and disruption. So the first one is, let's talk about one of the solutions, which is the use of relays. right? And basically, a relay is used to connect two moving elements. For example, a ground station on Earth with a spacecraft. In this case, let's say the International Space Station, which is in LEO, that is moving. So how you connect those two all the time? Well, you need a relay that has visibility to the International Space Station all the time and to a ground station all the time. Because just because of the orbit in which the International Space Station is, that there won't be permanent line of sight between the ISS to ground. But that same concept applied to any planetary surface. So, for example, when we're talking about Mars or even the Moon as a satellite, how you can ensure that a surface point on the Moon can communicate with a surface point on Earth 24/7 is primarily by using relay satellites. And one example is what I have here on the screen, which is NASA TDRES. It's probably the most famous relay satellite constellation, and that we have now that allows connecting elements in the different Earth orbits to the ground. TDRES is in the geostationary orbit and has been operating for quite some time. So remember, relay satellite allows to basically connect two moving parts, two moving elements. Then the second part is, how do we minimize those disruptions on Earth ground? Because Earth is also rotating, and there is a very geometrical solution to that, which is basically placing ground stations spread out around the world. And there are nuances in terms of what hemisphere, whether it is in the north or south, but using the most basic form, if you think about if you take one plane, what you do is distribute antennas, so you ensure that in a space you have 360 coverage. At minimum, you need 3 antennas to cover, or 3 stations to cover 120 degrees each, which basically is the case of the deep space network, where there is a complex in California, another in Australia, another in Spain. Sorry. And then from Earth and where you play, or any planetary body, but let's use Earth because it's where we have developed the satellite orbits. It's basically you find different places to place the satellites to have coverage of Earth, but also coverage of the other orbits. And we have the classical orbits, whether it is LEO, which is the medium Earth orbit, or the geostationary orbit, and then some specific ones which are the highly elliptical and polar orbits, etc., etc. And this is, again, making it super practical here. This is the ice.nasa.gov. I love this view. You can go at any point of time and see the deep space network and the different complex, and how they, how the different antennas are communicating to the spacecraft. So in this example, we are looking at the DSS 35 in Canberra in Australia, and that is communicating with the Mars Odyssey. And just look at this. The round trip light time is 26.5 minutes. So it's a very, very delayed communication. So how do we build this? So let me start with, again, in the How to Build Networks 101, we start with the physical layer. Physical layer means the radio link or the optical link. In this case, let's talk about radio. But the formulas are very similar, pretty much the same for any type of wave. And the way this works is pretty straightforward. Depending on the type of signal, that means depending on the type of encoding we're using, depending on the type of modulation, there is a minimum level of signal that has to be received by the receiver so that it is able to demodulate and extract information from it. And this is a very standard formula that says that the power that is received by the receiver equals to the power that is transmitted by the gain of the antennas, multiplied by the gain of the antennas, and then divided by all the losses, which is the space loss that is based on distance and frequency, as we said before, the losses that happens in the transmitter and other miscellaneous, and the receiver and other miscellaneous losses. And these losses has to do with cable losses, because there is a cable from the antenna to the electronics, and other type of losses. So this is where it starts. It's basically establishing the physical links, and the way you plan for that is doing a link budget. And the link budget is nothing else that putting numbers to characterizing the link, to ensure, and designing the link to ensure that there is always under very long range of conditions, there is always enough signal received so that information can be transferred. Information can be demodulated, can be. So if you go to descanso.jpl.nasa.gov, you're gonna see a great all the the communication link design for many of the interplanetary missions that has been launched by NASA over the years, and it goes to a very, very low level of detail, or very level of detail. So I encourage it for anyone who is interested into double clicking about how physical links are designed. Go there, you will find a lot of information. So think of it that we have a link established, and think of it that establishing a link allows you to communicate between 2 points. So now we see what happens next. So you have a link, there is signal, flowing through, but think of it that the main purpose of this is to transfer information. And you would say, okay, what type of information? Telemetry. And telemetry is the concept of data that is coming from the spacecraft. Then a commanding goes the other way around, which is what are the control functions that the human operators act on the spacecraft. So if you want the spacecraft to, let's say, move, or to activate or deactivate a specific sensor, these are control functions that are sent from ground to the spacecraft, and this is commanding data. And then you have data that is specific to tracking and navigation. Sometimes this data is just the signal itself. Sometimes it's bits and bytes that goes into basically the data flow. And last but not least, and this is a specific use, if you have a relay satellite, in this specific case, the purpose of the relay satellite is to relay data. Is basically the main use of the satellite is for communications. So in that specific case, the data may not be of use of the satellite, but might be of use of the ends where the satellite is connected to. In the case, it's a relay satellite. And depending on the type of data, you may imagine that the volumes may change, because if you think about telemetry, we might be downloading a 4K video. And in that case, the volume of data is pretty high. Or you may be downloading engineering or operational data that needs, the highest reliability. So that talks about the different levels that the data may be. It's could be high volume, high throughput, or it could be low volume but extremely high importance. And at the end of the day, this points to the fact that there are different classes or type of data when within a link. So with that in mind, CCSDS, which is the Consultative Committee for Space Data Systems, it's an organization that is formed by the space agencies, became a standardization body to basically enable digital communications with and through spacecrafts. And through that, there have been a series of protocols that were specified and are in use in space to basically create a data layer. Starting with, we already established the physical layer. So what happens then? The next step is let's establish a link layer, which is how two endpoints can transfer data between each other. And for that, you need protocols that specify the framing, that specifies, for example, multiplexing, that specifies security so that the communication between 2 points is secure. And that's what I refer to as the CCSDS legacy space protocol stack. This is basically the protocol stack that was created and have been created to enable spacecraft to ground and then a spacecraft to surface communications. And there are some popular modern protocols that, those that work on space data communications talk about, like, pretty much on a daily basis, like CFDP on the application layer to transfer files, or SPP to frame or format packets, to Proximity One, which is a proximity link protocol specific to space, or specific to the last, what we call the last mile. So now we get to this concept, which is, okay, what we have talked about enables, the establishment of a physical layer, and enables the establishment of a link to allow two endpoints to transfer data, digital data between them. Where we are right now is that there is, and this is already happening in LEO, and it's going to happen on the moon, and it's going to happen on Mars, is that the number of assets with communication needs is increasing dramatically. To the point that, when we talk about the moon and then Mars, there are going to be astronauts, there are going to be habitats, rovers, energy systems, and a very large number of support elements. And they will need to communicate between each other, with Earth, with different users on Earth for operation science, etc., etc. When, similar to what happened with the terrestrial internet, then managing this type of networks requires the concept of networking. And what is the big difference? The big difference is that with links, you can connect two nodes to a physical layer. With networks, you can automatically connect any node and any application that are connected to the network. And the interesting thing is that because each node has an address or a series of addresses, you don't need to know, as an end user, very similar to the internet, you don't need to know what is the path that the communication is taking. You don't need to worry about that. And that's the beauty of the network, or networking, which is it allows you to connect elements to the network, and then pretty much automatically, of course, security aside, you can get any endpoint to communicate with another endpoint. Networking is needed for a space in general. And the topic we covered today is interplanetary space. So this goes back to 1998. Basically a few experts, starting with Vint Cerf and many from JPL, Scott Borley, Keith Scott, and many others, got together in light of understanding how to provide automated networking with Mars, because of the fact that there would be a satellite in place. And they analyzed how the TCP/IP, the existing terrestrial internet architecture, would fit into it. And basically, the discovery and the conclusion was that the traditional terrestrial internet architecture had many architectural and performance issues that made it not suitable for its use at interplanetary distances. And some of those includes the fact that on Earth, because Earth is relatively small if you consider the volume of the space, internet is relied on infrastructure that is centralized on Earth, like DNS. Also, the protocols in general were very chatty and very connection establishment related, in which those protocols would stop performing in the presence of delay and or disruption. And in this case, 1998, the main use case analyzed was Mars. And all of that would rely on an architecture that would not guarantee a reliable transfer of data. And the solution to that was basically named as delay and disruption tolerant network. So what is DTN? or delay and disruption tolerant network. That its main purpose, as any networking technology, is to enable the reliable transfer of data across network elements. In this case, DTN network elements. When the propagation delay, the signal delay, is highly variable and or very high. In this case, the data transmission, because it is a network, it's performed automatically, even when one or more network links are not available during long time intervals. What that means is that the architecture takes care of the delays and takes care of, or is tolerant to, the disruptions. And even in presence of these two, the architecture can guarantee the reliable transfer of data between 2 points. In the case of DTN, the main internetworking protocol is called the bundle protocol, BP. The bundle protocol runs as an overlay network over multiple network or link technologies. So it's extremely flexible. For example, the bundle protocol in ground, as you see here in mission control, for example, can run over TCP/IP. Why? Because TCP/IP is fantastic, when we are on Earth. But it also can run over space, over link technologies and space protocols that are dedicated or specifically designed for the space scenario. So, for example, you see here that in deep space, the bundle protocol may run over the glider transmission protocol, which is LTP. And there are other, other designs and other convergence layers, as it is termed. The second part of it is that networking, in general, is support scheduling, which are basically planned contacts. Saying, one of the good things about the space is that we can pretty much predict with very high level of accuracy when a specific point on Mars is going to be on line of sight with a specific point on Earth. So we can design with very good accuracy the schedules of communication. So the networking side, networking supports schedule contacts, or also opportunistic contacts. This is in case of the system can also work with signals that says that the links are up. And one of the things that is also very particular to the bundle protocol, with respect of traditional TCP/IP technologies, is that the networking layer itself performs store and forward. Why? Because, as you know, and as we have been talking about, there may not be a link between one node and the next node for a while. So what do you do with the data that is incoming? You have to store it so that it doesn't get lost, right? So the networking performs store and forward. Every node has the capability to store data. And this is, I don't know if it's going to play well, but this is basically it's not going to play well, sorry. This is disabled, but there is a good, I'm going to look at the link and send it later, but there is a good animation that compares TCP/IP, UDP/IP, and DTN in presence of disruption, and how DTN is able to support a reliable transfer of data at any, DTN hop. So where are we? There have been great progress since 1998, where the first idea of the architecture was put together. There have been great progress on DTN and the establishment of the interplanetary internet. And just put some experimental highlights. I won't go into a lot of detail, but those the experiments got to a point or went from initial experiments like the successful DTN experiments performed by NASA with the approximation in deep space, that basically was an 81-second delay, successful experiment, to basically controlling applications like the experiment of controlling a robotic arm through DTN performed by ESA on the ISS, to basically the setup of the first ever operational network in space with on the International Space Station, and that network is already still up and running on the ISS. It's basically managed by run and managed by NASA, to the point where other organizations, came in, started with the IPNSIG. The IPNSIG established the pilot project working group, established the first civil open DTN ground network, which is still in operations, and many of you can join if you decide to do so. It's our first attempt to have an open DTN network. Then in 2021, the DTN, as a commercial company, performed experiments on the ESA OPSAT satellite on LEO, performing interoperability tests between macro DTN and ION, and performing with the help even of IPNSIG members, performing a cloud vision application through a ring road, basically a data mule using DTN. And then in this year, many highlights. The PACE mission, which is an environmental satellite, is the first ever NASA Class B mission that used DTN operationally in a satellite. That's up and running. At the SPATIAM, we performed the technology demonstration in that International Space Station this summer very successfully, demonstrating a commercial DTN platform for space. And very, very recently, Scott Johnson and Spacely Packets perform a prototypical implementation of email service over Wonder Protocol. So where this is going, basically this is going to full operations at a scale. And the big target is LunaNet. LunaNet is the Lunar Communications, Position, Navigation, and Timing Network Architecture Network Framework for the Moon, which is sponsored by NASA, the European Space Agency, and the Japanese Aerospace Exploration Agency, JAXA, with support of other organizations and the commercial industry at large. DTN is the main internet working protocol for lunar networking and lunar communications. And even beyond that, LunaNet is establishing the concept of LunaNet service providers, which is very equivalent to the internet service providers on Earth, but it's basically providing communications and or PNT, position, navigation, and timing services. And there is a whole architecture to how to connect users to the network and how to connect network to network to ensure, the main purpose is to ensure interoperability so that end users can have reliable transfer of data through the network. So that's going to be a major formal steps towards, or the first phase of the interplanetary internet, fully operational as we know it. So that's fully in motion, both from the Moonlight project on ESA, also from the NASA perspective, and in collaboration with many commercial organizations and other institutions as well.